Hi, my name is Muhammad Adik Fauzan bin Muhammad Zahiri. My matrix number is 2023817832.
Hi, my name is Muhammad Shauki bin Othman. My matrix number is 2023668196.
Hi, my name is Risha Alia binti Shamsul Mazli and my matrix number is 2023681962. Hi everyone, my name is Risha Alia and I will present to you on the topic of differentiation in calculus. Let's begin with some background information to understand the importance of differentiation. So, what is differentiation? Differentiation refers to the process of finding a derivative of function. The derivative represents the rate at which a function is changing at any given point and is a measure of how a function output value changes as its input value changes. In simpler terms, it's about understanding how a small change in the input of a function affects its output. Now, let's look at some real-world applications of differentiation. One important application of differentiation is in solving applied maximum and minimum problems. This problem involves using calculus to find the highest or lowest value of a function within a specific context, such as maximizing profit, minimizing costs, or optimizing efficiency. By finding these critical points, we can make informed decisions in various practical scenarios.
Why we use applied maximum and minimum in our daily life? Firstly, we use applied maximum and minimum problems for efficiency by identifying optimal solution. It ensures resources, for example, time, money, materials, are used efficiently and effectively. Secondly, it's for solving practical problems where it helps us find the best possible outcomes, such as maximizing profit, minimizing costs, or optimizing efficiency. Other than that, predictive modeling, for example, it helps in forecasting outcome and understanding the behavior of systems by analyzing critical points. So, let's proceed to the next session where we are given a problem that needs to be solved by using applied maximum and minimum method. Given a rectangular box with a square base and no top, is to have a volume of 108 cubic centimeters. The question is find the dimension for the box that require the least amount of material. The function that is to be minimized is the surface area, S, while the volume V remains fixed at 108 cubic centimeters. Let's break down the problem piece by piece. First, as the problem states, we need to find the dimension of the box, which means the length, width, and height. So, we need to find the formula for volume by expressing V in terms of X and hash. Why only two terms? Because the surface of the box is square, which means the length and width have the same value. After analyzing it, we come out with V equals to X squared multiplied by hash. Next, we need to find S formula. We need to be very careful as the problem states that the box has no top, which means there are only 5 surface area of the box that we can find. As a result, we have come out with S equal to 4 multiplied by X and hash plus X squared. We know that the volume is 108. Substitute the value into V function which we created earlier. Next, we need to express hash in terms of X. Hash equals to 108 over X squared. This function will be used in the next step.
The problem gives us the volume of the box, which is 108 cubic centimeters. This value needs to be substituted into our inertial volume formula. By doing this, we can express the height, which we call h, in terms of the side length, which we call x. Once we have h expressed in terms of x, we substitute these expressions into the surface area function, making the function depend only one variable. After the substitutions, the surface area function as in terms of x become s equals 432 divided by x squared plus 2 times x. This streamlined approach allows us to work with a single variable, simplifying the problem and making it easier to solve.
Now, this is the time we apply the minimize and maximize application to find the value of dimensions. The differentiation of S is set to 0. Why? Because a derivative is just the rate of change of the function, or in other words, the slope. After the process of substituting the 0 into the derivative of S, we could find that x equals to 6. After that, we can substitute the value of x into h function to get the value of h, which is the answer is 3. Finally, we got the dimensions of the rectangular box that has no top on it without changing the value. Take note that we are only find the dimensions of the box without knowing whether the values is maximum or minimum. So this step is crucial to determine the values we got earlier being maximum or minimum. We need to use the second derivative on function s and substitute the value of s that we have already got earlier, which is 6. Actually, at this step we want to test the value of s. That's why we substitute 6 into the second derivative of s. When applying the second derivative, what we need to focus on is the result of substitution, whether it is greater than 0 or less than 0. If it is greater, the dimensions we got is a minimum value. If it is less, the value is a maximum value. Okay, after applying the second derivative, we got the result is 864 over x cubed plus 2. By substituting 6 into the function, we got the result is 6, which is greater than 0. This concludes that the value of x is minimum. In conclusion, minimizing the surface area of a box with a fixed volume of 108 cubic centimeters involves finding dimensions that maximize efficiency. By leveraging calculus, we derive the dimensions, which is length, width, and height, that minimize material usage while meeting the volume requirement. This approach optimizes resource allocation, ensuring economical production and effective utilization of available space.